Recording is rolling. It is Monday, January 13th. Welcome back from the weekend. All right, so I remember back on Thursday, Friday, you guys had that torque lab. You guys remember that? You had a seesaw version on Thursday and a scaffold version on Friday. Hey, this setup looks pretty similar. Look at that. Here's it. What's the tension in the cable? Here's a cable holding a beam that's at this pivot point joint fixed to a wall. You guys see that? Okay. So guys, if this cable wasn't here, what would this beam do? Would it just fall down clockwise, like that? But the cable's holding it in place. What's the tension? So there's your starter question there. Looks pretty similar to your lab on Friday. Then I have a spool demo lined up for you guys. So we'll look at this. Yeah, all right, so got some challenge questions related to how's the spool going to rotate. Okay. I'm going to introduce a new concept to you guys today, angular momentum. So you guys definitely have your notes out because at least you're solving this one. But later today, look at angular momentum. It's going to explain tops, gyroscopes. I got a coin demo for you guys. I also got a whole bicycle wheel here, so that's going to show up class later today. Okay. All right, so angular momentum. Got some Paul Hewitt demos for you guys. On your desk, there is probably a foam board with some points on it. So that'll be an activity about the last 5 minutes of class. I'm going to have you guys find the center of mass. All right, so we'll do that too. Yeah, it's a pretty ambitious plan. I won't have time to get to, this bit that I crossed out, so we do that. Right here, I'll mention some details about AP, even though you guys in front of me are not AP, but just for all my classes. My AP students have AP Classroom Units 5 and 6 due Tuesday and Wednesday morning, respectively. All my classes, I did give out textbook puzzles last week, which we haven't quite got to yet, but chapter 8 from 3 different books, they all align to chapter 8 for this rotational dynamics. All right, so yeah, there's a broad overview of what we're doing today. All right, so let's look at this setup here with this beam and this wall, and this pivot joint, and this cable. All right, so I'm gonna copy this over. I bet you guys already have a head start on me, right, drawing this picture. All right, so you guys already probably got it drawn. So I'm drawing it. Let's get a head start. Okay, so here's my wall. I'm gonna hatch off this wall. Okay, you got this beam. It's got some length. Okay. Now, here I wrote length 3 meters. Right. Thinking ahead a little bit. Turns out I could have made this length anything. The length doesn't matter. As long as these angles are the same and the weight is whatever weight, so gave 100 newtons weight. Right. The tension in the cable is going to be the same regardless of the length. Right. As long as these angles are still the same. Right. And just a little thought right there. Right. What's the tension in this cable? Right. So I'll label this cable. So I got a pivot point right here. Here's my pivot point joint. Right, so yeah, if the cable wasn't there, it would just fall down. Okay. How about the weight of this beam? Guys, is the weight of the beam distributed over the entire length of the beam? Yeah, it is. Right. Now, when I go eventually gonna make an equation to solve this. Right. When I set up an equation, is it okay to make believe that the entire weight is at a single point at the center of mass of the beam and then treat it mathematically that way? Yeah, that's perfectly fine. But you guys did a similar thing last week when you guys had the torque lab. You guys had a meter stick, hold up some spring scales, and maybe you hang another weight from it. But the meter stick itself had some weight, and you would treat that all as if it was at the 50 centimeter mark. Because the geometric center could be also the center mass, as long as it's distributed uniformly. Right. So I'm going to use pink ink for all my force vectors. I just told you guys. I really only gave you one force, and that's the weight of the beam. So say mg, the weight, is 100 newtons. 100 newtons weight beam. Okay. I told you the length here could be 3.0 meters. So we got that. Okay. What else? I gave you some angles. I said this angle down here is 60 degrees, and this angle up here is 30 degrees. I don't think my picture is exactly to scale, but you guys get the idea, right? Okay. And this could be a 90-degree angle here. Okay, got that. 30, 60, 90 looking triangle. Okay. All right, you guys get all that? Okay. And we're trying to solve what is the tension in the cable. All right. I think I have all the relevant necessary details there. Yeah. Okay. There's like a pivot joint. I'll go ahead and label this I got a pivot or joint. Let's see, like that. Like that. All right. So, let's see, what framework of physics should I use to solve this? Let's go through 3 frameworks. Guys, Who thinks this looks like a conservation of energy question? Does this look like conservation of energy? No. Does this look like conservation of momentum? No. Does this look like kinematic motion? No. Does this look like equilibrium? Aha! Bing! Equilibrium. Equilibrium. All right. And if you remember, is what are the conditions for equilibrium? The sum of what goes to what? Sum of force goes to zero. Sum of force goes to 0 newtons. Okay. Now, if this is a 2D puzzle, this looks like 2 dimensions. Maybe you could say sum of forces horizontally goes to 0, and the sum of forces vertically goes to 0 newtons. So sub x, sub y, horizontally, vertically. But also one more condition. The sum of what else also goes to 0. What were you doing back on Thursday and Friday? Torque. Aha. Torque goes to 0. And that would be Newton meters, right? So here's your conditions for equilibrium right here. Equilibrium, right? As long as it got all those going on, right? Like this would all be true, right? Remember, I was telling you guys too, if you're doing civil engineering someday, then this could be the starting point of anything you design. Now, if it's in 3 dimensions, you got a lot more axes, but everything is going to zero out, right? Forces and torques, right? So let's go back to this diagram here, because I gave you one force, but I bet there's more forces acting on this beam. Let's look at all the forces acting on the beam, right? Sometimes I'll call this free body diagram if you're labeling the forces. Now, AP, they distinguish between that and what they call a force diagram, where they have specific locations for the forces to act at, right? Now, last semester, you put all the forces through the center of mass, but this week, last week and this week, it matters the locations of these forces because it's going to set up torques. If you have different forces at different locations on an object, you can get torques, right? And that's part of this, okay? So there's definitely some tension in this cable here. I'll call this F sub T for a tension force, right? That's what we're solving, right? What's tension force? Right? Guys, are there any other forces acting on that beam? Is that the whole story? Or is there something else going on? I don't think this can be the whole story. And here's why, what I'm thinking. Guys, what if I split this tension into components? Say, how much is the cable pulling up versus how much is it pulling the beam towards the left? Okay. Ooh, that's a nice little triangle going on there. Guys, what is this angle right here? 30 degrees. What's this angle up here? 60 degrees. Right, so another 30, 60, 90 looking triangle. That's it, right? And then, guys, would this component here be whatever the tension force, and I still don't know the tension force yet, right? But whatever that is, times what? Could it be either sine of 30 degrees or cosine of 60 degrees? Because those are the same thing. Okay. Actually, I bet you guys know sine of 30 degrees. What is that exactly as a ratio? 1/2, right? Right. So if my picture was to scale, this segment, this like should be half of the hypotenuse of that triangle. Right. All right. And then this one here, could this be ft times cosine of 30 degrees here? Right? Or sine of 60 degrees. You could also say that if you wanted to. Same thing. Okay, I said. Okay. All right, so guys, look at my conditions for equilibrium. Here's the first condition. Sum of forces horizontally goes to 0. Hey, the fact that the cable is pulling the beam to the left and this beam is supposed to be in equilibrium, I think I'm missing some forces. At least one force. Doesn't there have to be a force resisting the cable pulling the beam to the left? And what force is that that's balancing that out? The normal force from the wall, right? Doesn't the wall push back, right? So I'm going to, from the wall, put some F sub X right here, right? And if, should this to the left and this to the right exactly zero out? Yeah, because that would match this condition right here, right? Right. Here's another thing. Guys, what if you took this pivot joint out and you held it up with your hand? Like, hold it up with your hand. I mean, you would have to apply an upward component of force too, right? Right. And that kind of reminds me of your lab back on Friday. You guys had 2 spring scales holding up the meter stick and some weight kind of in the middle. So I'm going to say that there's also a force up here. I'll call it F sub Y. Now this is from the wall, and this is F sub X from the wall, or maybe from that pivot joint, whatever. Say wall, whatever. Right. Now really, that's 2 individual forces. or sorry, scratch that. Sorry, that's probably two components of a single force. I bet if I drew that as a single force, really the pivot joint is pushing just up to the right overall. So I never really draw components as individual forces, but I'm kind of breaking one of my own rules here. So I'll pretend that's like two separate forces because mathematically it's kind of like that. Right? All right. So now I think this is sort of a complete force diagram on the beam. Force diagram on this beam. All right, just write the word beam out here. This beam going out here. Okay. All right. So now what? Well, I really only know one force, and that's the weight of the beam. Right? Don't know any other forces, and my goal is to figure out what is this tension right here. Is that? Right. Right. So then I could set up different versions of equations with any of these three conditions. But I'll tell you guys what, I can solve this whole question. So what is the tension of the cable with just one equation? Okay. Guys, if I can solve this whole thing with one equation, which of these conditions do you think it would be? First, second, or third? Third. Yeah, it is the third one. Right. Here's why it can't be the other two. Right. Like, well, you could solve it. Well, sort of, but you need more than one equation, right? Because in the x direction, see, there's two unknowns there. In the y direction, there's two unknowns and one known, right? Guys, can you solve two unknowns with one equation? No. Right? You need two unknowns, two equations, three unknowns, three equations, right? So if I want to solve this one equation, I need to somehow set up an equation with only one unknown. And you can do that with this torque condition right here. You can do it, which is what we're about to do, right? If you correctly choose the pivot point to sum the torque about. Because which point looks like mathematically, or maybe just intuitively, a nice point to choose as the pivot point for your torque equation. Which point do you want to choose? How many of you guys think? Here, show hands. How many of you guys think it's this point right here? This point right here. Yeah, there's my winners right there. Right. Here's why. Guys, if you choose this as your pivot point, which you may pick intuitively anyway, right, here's why it's nice mathematically. Two of your unknown forces are acting right at that point. Therefore, in terms of torque, how much force do those points, if I walk over to this door and I start pushing on the hinges, how much torque am I causing on the door? Nothing, zero. Yeah. So mathematically, they go away. Right? And then the only torques are caused by, well, I got this weight and this cable tension. Okay, and I can solve it like that. Right? So let's treat this as my pivot point right here. Right? So this pivot joint. Okay? Now at that point, I say what torques are being caused. Now the weight of the beam. Now, and I said, like if you cut this cable or took the cable out, get rid of the cable. Okay. Just the fact that the beam has a weight, it wants to rotate how? Clockwise. You guys see clockwise? Right? So the weight of the beam at this distance from the pivot point is causing a clockwise torque. Right? Remember, I'm gonna treat the weight as it's all through the center of mass of the beam, and mathematically that's perfectly fine. Right? This cable pulls back which way? Clockwise or counterclockwise? Counterclockwise. Okay, so that's ooh, hey, there's two torques. Do you think these two torques exactly zero out? Yeah, and that's gonna lead to this equation we're gonna set up right here. Let's set up a torque equation. Okay. So now you guys remember, of course, torque equals R cross F. Or I should have asked you guys. You guys would have said that, right? Torque equals R cross F, right? And we have two of them. Looks like we got one clockwise, one counterclockwise. They're going to zero out. Okay, that's the whole premise right here. So let's do R cross F. Okay. Guys, what is this radial distance right here? 1.5 meters. Yeah, because it'd be half of 3 meters, right? I told you the length of the beam is 3 meters. So 1.5 meters out. So let's do 1.5 meters times 100 newtons force. There's a torque, right? Also, since that's clockwise, I'll work in a negative sign. I don't know, maybe down is negative, negative. I'll pull a negative out. I'm going to make it negative, right? I'm going to call it clockwise negative. That usually you do, right? If you did right hand rule, you do R cross F. You'd be pointing your thumb into the page, okay? Which would be the opposite of what this cable's doing. This would be R cross F. It'd be my thumb's pointing out of the page, right? I'm not going to use right hand rule so much, but you might see that more in college. So if you do right hand rule, right? But we're going to stick to clockwise, counterclockwise, right? So I'll say plus, and then at a radial arm of the full 3 meters, I have, well, times what? Because what force should I put right here? the tension force. Now, is it the full tension force? Guys, what does cross product mean? Cross product means you only count the what components? Perpendicular, right? So it's not the full tension force because it's off on some 30-degree angle from the vertical. Okay. So, guys, it's tension force times what? Cosine 30 degrees? Is that? Or again, you could say sine 60 degrees. You could say that too, right? So tension force times either cosine 30 or sine 60, same ratio, both root 3 over 2, right? This all goes to 0 Newton meters. There's the setup right there. That's the setup, right? And notice it's one equation, and it only has one unknown value, which means you can solve it with algebra. You guys get that so far? You guys okay? We're doing? Okay. Yeah, so this looks, again, a lot like your guys' lab back on Friday. The main difference is instead of the two spring scales both pulling straight up, okay, now you got the cable pulling off on an angle. Okay, so we're bringing in a little bit of trigonometry, but otherwise it's pretty similar to what you did back on Friday. All right, so let's finish some algebra here. Algebra 1.5 times 100 is 150. I can slide that over to the other side. Right. Then I got, okay, so 3 meters times the tension force we're solving for times cosine 30 degrees equals 150 Newton meters. Okay, so you take the 3 and the cosine 30 degrees, divide each of those down. 150 divided by, and then open parentheses, 3 by cosine 30 degrees. Do you guys get that? Just a little algebra shuffle. Oh, before I hit enter though, right? I want to backtrack a little bit because some of my other classes I had them frame the question different ways before we actually started plugging and chugging with equations. Okay, so let's think about this in terms of forces. I know I'm backtracking a little bit, but I want you guys to predict what a reasonable answer would be before I hit enter on this calculator. It's like all I have to do is hit enter. But let's see. Okay. Guys, in terms of forces, what if I change the orientation of this cable? Guys, what if this cable is pulling straight up? Guys, if the cable's pulling straight up, I bet you guys can get the answer right away. How much tension would be in the cable? 50. Yeah, exactly. Because it'd be 50 up here, it'd also be 50 up here to balance out this 100 down here. And that would look just like your guys' lab back on Friday, wouldn't it? Right? And the fact that I have the cable then oriented a little bit to the left, okay, so I know this upper component actually should be 50 newtons. This Ft cosine 30 degrees should be 50 newtons. Okay. Therefore, the full tension of the cable is it a little bit more or a little bit less than 50 newtons? It has to be a little bit more. You guys remember one of the labs I had you guys do last semester? Took some spring scales, pulled up a weight. You spread the spring scales out to like a Y shape and then a T shape. The more you spread them out, the more the force was, right? It's kind of like this too, right? Right. So when I get to this last algebra step, tension force equals, right? When I hit enter on this calculator, I do this, divide down these, right? I should get a little bit more than 50 newtons. Do you guys think? A little bit more than 50, right? Would be reasonable, right? Let's see. Look at that. 57.7. What unit? 57.7 what? Newtons, because it's a force. That's right. Forces in newtons. And it is a little bit more than 50 newtons, isn't it? So that does look like a reasonable answer. Yes, that's got to be it. All right, you guys think that's the answer right there? Okay, I think that's the answer. All right. All right, are we good? That's good? All right. Oh, next thing, let's do the spool right here. Do the spool. All right. All right. So if you guys see, I got a string wrapped around that small circle on the inside, small diameter. Okay. But this large diameter circle, maybe you could roll around the outside. Okay. See it? Okay. So I'm going to pull the string a few different ways. First, I'm going to pull it straight up. You guys see I'm pulling the string straight up? Right. Now, when I let go with my left hand and just pull the string straight up with my right hand, which way is this going to rotate? Let's say either to the left or to the right. Okay. Show of hands. How many of you guys think if I pull straight up with the string right now, it's going to rotate to the left? Who says to the left? Right? Does anybody say to the right? I saw a bunch of hands to the left. All right, let's see. Right. So pull straight up. It is to the left. I think everybody got it. Everybody got it. It is to the left. Right? All right. So let me draw that out because I'm going to change some things in a minute here. All right, but start with, I think you guys all got the straightforward question. Got the spool. It's got this inside circle. The string is wrapped around. Zip, 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 right? And see, this is on a table surface that might be about to be important, so I'm going to draw that in. Okay. And first thing I did was just pull straight up. I call this FT for tension force. Okay. And it did rotate counterclockwise off to the left, just like you guys said it would. All right. All right. You guys ready for a challenge question that, well, it's been about 50-50 all day today? You guys ready? All right. So he's going to figure this out. All right. Yeah. Well, if you guys like my other classes, but it's going to be maybe a 50-50 split. Let's see if you get this right. What if I pull this straight horizontal? Right. So here, I'll even draw it out before I do it. Right. So I'm going to pull this way with the string. Call this F sub T, the tension force pull to the right. You see that? Okay. Now, what's going to happen when I pull this to the right? Okay. So same options as before. Either rolls to the left or it rolls to the right. Okay. Show of hands. How many guys think this is going to roll to the left? Who says to the left? Right. Who thinks it's going to roll to the right? It's to the right. It is about 50-50 split. All right, let's see. Let's find out. It's to the right. Look at that. I pull to the right. It rolls to the right. You see that? Ooh. Okay. Now, if you said to the left, I bet what you were thinking is that, well, okay, we got a circle. Looks like it's rotating maybe about the center. Like if we put a left X in the center, right? And I know torque. Is R cross F. Okay. So let's say I got this radial arm crossed with this force, and oh, yep, that looks counterclockwise, just like the first one. Except that's not what happened. Okay. And the reason is that, guys, this wheel is not actually rotating about the center. This wheel is rotating about which point? Aha, the bottom right here, right? Actually, you need another force to make this happen, to make this rotate that I haven't drawn yet, which is a friction force. Okay? Yeah, there's two forces at the bottom here. There's the normal force in the table. If there's a normal force, there's allowed to be a friction force acting the other way. Okay? Guys, for something to have a torque, you need a radial arm separation between two different forces acting on it. Okay? Like even just opening a door, the hinges are locked in place, so there's like a counteracting force there, and then you're pushing on the handles, and they're separated. Those forces are separated by the width of the door R. Right? Or like turning, using a wrench to turn a nut. So same idea, right? There, yeah. So this wouldn't actually rotate, except that there's a friction force down here, which is allowing it to rotate. Okay? So the first time when I pulled straight up, here's your radial arm right here, R, which would have been the same even if you thought it was through the center, because that looks like the same thing, doesn't it? Right. Okay. But when I pull horizontally, you got to be careful, because if you thought it was from the center, you actually would have gone it backwards. It's not that one. It's actually from this point right here. This is the actual radial arm causing a clockwise torque. You guys see that? Right, that's what actually happened. Right. Everybody good so far? Right. All right. Here's an extension question. Because if I pull straight up, it rotates to the left. Pull straight to the right, it rotates to the right. Counterclockwise, clockwise. Okay. You guys think I could orient the string somehow in the middle where there's no rotation at all? Right? And if it's somewhere in the middle, there would be a rightward component. Hey, I bet I could get this thing to slide to the right without any rotation. You guys think I could do that? Huh. Let's see if I can find the point. Right? Now, see if you guys can. There's a reason I got a blue sticky note. I want you guys to see that blue sticky note. It's not going to rotate if I get this at just the right angle. Let's see if I can. Yeah, just the right angle. This blue sticky note does not rotate. Ah, there it goes. You guys see it sliding without rotating? Sliding without rotating. Look at there. You see that? Okay. And if I draw, let's see, where should I put that? I bet this would be probably about that direction right there. And I know that because of this. If I extrapolate backwards, hey, look at that. You guys see extrapolates backwards exactly through that pivot point, right, where the friction force is acting, right? Now there's still a normal force and a friction force, right, acting at that point. And this tension in the string also extrapolates back through that pivot point. That's like having a bunch of different forces on the door hinge of a door. It'll never rotate the door. Ah, so this whole wheel is allowed to slide without rotating. Is that? Okay. Here's another extension question. Guys, what if I wrapped around so much string that completely filled the inside and like bulged out the outside and went like beyond, right? And then I got like open up a space underneath and I pull. Now what? Okay. And I bet if you follow this, you think about the application, you might be able to figure that out. It's a little tricky question, right? But here's what I'm going to do for that one. Do you guys know a YouTube channel? A guy named Steve Mold, maybe? Right. Some of my earlier classes did, right? He does a bunch of science engineering stuff on YouTube. I'm going to post a YouTube video where he does this experiment, right? But he also does that extension question I just asked, because what if you have like so much string that it actually like bulges outside of the large radius, large diameter circle, right? So I will post that if you want to look more into that spool question, right? Okay, guys, good. All right, so if I go back to my agenda here, we did check, solve this, we did spool demo, check, right? We're gonna move on to a new concept. You guys ready to learn something new? So angular momentum, you guys ready? Right? All right, so this is gonna be momentum in a rotational context. Right? Here, we'll start with some notes and then I'll do some demos with you guys. Okay, notes and demo, or well, here, I'll do a few quick demos because I got a few demos, right? So I got a gyroscope, and I don't have the string right now with the gyroscope, but if I get the spinning fast enough, you guys have ever played with the top, right? You spin a top, it stays upright, right? Or I got the, so I can't spin this fast enough with just my fingers, but how about this coin? Right, guys, look at this quarter. You guys ever try to stand a quarter on its edge? Right, it's nearly impossible to do. Guys, how can I get this quarter to stand upright? Yeah, spin it. Look at there. It'll stay upright for a while, right? Okay. And part of this explanation has to do with a property called angular momentum. So here, I'm going to put this page into quadrants. Okay, maybe quadrants. Take up a full page just for the camera, but however you want to put this in your notes. Right, so if I go back a few weeks ago, I have linear momentum. Like what was that? And then momentum, right? We'll say what's analogous to that in a rotational sense. I'll call that angular momentum. Okay. And then we'll talk about impulse. Remember that was a change in momentum. Okay. And then what's the rotational version? Angular impulse. Okay. So we'll do all of these. Okay. So let's go back to a few weeks ago. Guys, what was the formula for momentum? What times what? Was it mass times velocity? Right? MV, P equals MV. You guys remember that? Okay. This was the property that was conserved during collisions. You guys remember collision carts, the whole deal? MV. Right? Okay. Right. Vector. Because on this page, anywhere I put but what does this arrow mean above the letter? It means it's a what quantity? A vector quantity. So direction matters. Okay. Notice I did not put an arrow above the M because mass is a scalar. Okay. Now, if I do the rotational version of this, right, if something's rotating, got this coin spinning, got something like this. I'm going to call this capital L. And this is going to be a vector. Right? It's a property that has a direction associated with it. Right? Equal to, see, what times what? I think you might be able to figure this out. Okay. Because mass in a linear sense represented how much inertia something had. Okay. You guys remember last week, I passed around a couple of meter sticks with weights tied to them, and you shake them back and forth, and they have different rotational inertia. You guys remember that? Right? And there was a whole table of values depending on how mass was distributed. Like this basketball might be close to a spherical shell. So, okay, and a bunch of other shapes too. Right? And guys, what was the physics character for inertia in a rotational sense? What letter are we using? I. Yeah, I, capital I. Right? So for a point mass, it's mr squared. And then if it's any other shape, it's just the aggregate of all those points mr squared. Okay? So how much mass, but also how's that mass distributed? Okay? And multiplied by, ooh, and guys, what's the rotational version of velocity? What letter is that? And it might be Greek. Omega? Guys remember omega? Okay. So V linear velocity could be in meters per second. Omega angular velocity could be in radians per second. You guys remember that? Right? Okay. So if I do I times omega, so how much rotational inertia does this have? Trying to rotate. Suppose you have a turntable, right? And how fast is it rotating? That's a property called angular momentum. And that wants to be also conserved, kind of like linear momentum wants to be conserved. Okay. Let's look at the impulse versions of these two, because these are going to show up in the posters later today. Okay. So impulse, that could be a change in momentum, which could be mass times change in velocity. And you get that by applying a what for a what. You guys remember a bat hitting a baseball? You guys remember that? Right? Bat hitting a baseball? Right? Because that was what times what? Force times time. Yeah. apply a force for some time interval. Okay? If you see a graph that's force versus time, then the area under that curve represents impulse, the change in momentum. Okay? All right, so finally, this last quadrant here, what's the rotational version of this? And you'll see this in some posters later today, pretty soon, a few minutes. Okay, so a change in angular momentum, delta L. Okay, that could be I times delta omega. Okay, so maybe you have a turntable and you're speeding up or slowing down and rotating. Okay, so I'll show you guys a picture in the PowerPoint pretty soon, what they could look like. Okay. And that comes from applying a what for a what. Take a guess. I bet some of you guys might be able to figure this out. Look at what's analogous to what. What do you think goes right here? What times what? Torque times time. Yeah. So what a force represented in a linear sense, a torque is going to represent in an angular sense. Oh, let me put little arrow vectors above my vector quantities, right? And for some time interval, torque times time. So if you apply a torque for some time, you're giving something in angular momentum. Okay? You guys see it? All right. Here, I'm going to do this bike wheel demo, and then I've got a Paul Hewitt demo, and then we'll do some slides. So you guys see this bicycle wheel? All right. Now, if you're watching this video at home, then use your imagination a little bit. But I'm going to spin this bike wheel and watch what happens. Watch what happens when I don't spin it versus I do spin it. It's going to be weird. Okay. So if I don't spin this and I hold it at the edge here, it just falls straight down. You guys see it fall straight down? Okay. But you guys want to see this thing levitate? See levitate? See some physics magic? Some wizardry going on here? Give it a spin and look at that. It levitates. You see it? But notice it's also processing around a little bit. Now, what if I grab it at the other side? See what happens. Still levitates. Oh, but look, now it's processing around the other way. Look at that. Okay. How about this? What if I stand on this turntable and do the same thing? Okay. Now, right now, see, like, okay, if I move back and forth, it takes a little force, but not too much. Right? But give this a spin. I feel some resistance change motion. It does not want to change its orientation. I feel a resistant motion. If I stand on the turntable, look at that. It's like driving me around. It's just like changing direction. Right? Now, here, there's a lot of vectors going on in terms of forces and torques that's causing this weird rotation to go on. So I only got so much class time today and concepts I want to go over. So here's what I do is I'm going to post a video on Google Classroom that is a Vsauce video. Here, this one right here. You guys see he's basically has exactly what I was just doing. Right? Actually, I think I posted this also last semester. It's called Spinning. You guys maybe watch this one if you watched last semester. Right? He does a full explanation of why that levitation happens. Right? I will also post. Oh, look, you guys see this full video right here. Here's the Steve Mold channel. Right? So he's gonna do that extension question of like, what if he winds this and it goes beyond that diameter? Right? So I will post both of those links to Google Classroom later. All right, let's find that Paul Hewitt video on angular momentum. Here we go. Here's a classic right here.
It's a very low friction rotating platform. What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotation inertia or a little? How about when I pull them in? A little? So if I get here rotating like this, and I hold them out, what happens when I pull them in? Ooh, easier to rotate, gang. Harder to rotate. Easier to rotate. Okay. You see such thing? All right. All right. You go to the you go to the ice bollies, you see the skaters turning around like that, they're spinning. And when they're spinning, they pull in like this, yeah? Go fast, and then they come on. Da, 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 da. And people think they're going like that for applause. You know what they're doing? They're trying to save them from breaking their necks. You increase your rotation. Isn't that neat?
Yeah, that is pretty cool. All right, let's do some slides here. Okay, so I'm going to rewind way back to a little bit of recap from last week, and then we'll get to some new stuff. All right, so you guys remember this rotational inertia sticks. So rotational inertia, mr squared. It's not just how much mass, but where's that mass located? Mr squared, sum of them are squared. There's some rigid shapes. If you aggregate effect, like this basketball, it's a factor of 2/3 mr squared, and so on. So we got that. Right. We get parallel axis theorem. Right. Ooh, torque, R cross F. Right. We've been applying this the last few days in this class. Just a couple labs, Thursday, Friday, torque. Right. Now, this right-hand rule and this matrix determinant math, in place of this, we're just going to focus on clockwise, counterclockwise. AP does the same thing. They ignore right-hand rule and matrix math, and they just go clockwise, counterclockwise, right? But you might see right-hand rule in college, right? So is something into or out of the page, right? Here, I think we got an extra minute. I'm gonna take an extra minute and show you guys what I mean, right? So, right, if you have this, let me find my picture from before, right? Like this cable right here, right? Relative to this pivot point at this joint with the wall. Here's your R, here's your F. You guys see my thumbs out of the page, right? Versus the weight of the beam. Here's R and here's F down. You guys see my thumbs pointing into the page? Okay. Yeah. Again, not really our context for this class, but you might see that in college, and that's actually mathematically a better way to handle that. All right. So let's get past. Okay. We'll do this lab later this week. Rotational inertia. Hey, look at this. We just solved earlier today using these equilibrium conditions. Okay? If you go into civil engineering, this is your starting point for any design you do. You just have to satisfy these equations, right? So like 3D, just the 6 equations on the right, you can figure out every component, everything you're working on, right? Here's your lab back on Thursday with the seesaw, right? Here's your lab on Friday, scaffold. Right, so you guys did those labs, right? Okay, lab table, right? Ladder against a wall. Hey, that's the one we solved earlier today. Did we just solve this? That's your notes from earlier today, isn't it? Right? I bet we've set up an equation that looks a lot like this green box down here. Right? You guys think? Also, your textbook questions. This textbook question looks like that. Also for AP, I think they have a hungry bear walking towards a basket of goodies, so you have to consider all those weights and torques also. A little more involved version of that. Got that? Okay. All right. All right. Now we're kind of bridging to some new stuff. Okay. So, guys, what if I wind a string around a turntable and I pull with a force? Zoom. You see that? Pull with the force. Okay. Now, guys, if there's a constant force, shouldn't there be some kind of acceleration kind of motion? Do you think that turntable speeding up spinning? Faster, faster? All right. Let's see, what are the equations here? So torque is R cross F. So this R crossed with this F. Okay. That's going to result in some I times alpha. Okay. So R cross F results in I times alpha. Okay. What is I for a disk? Well, I'm going to rewind. Rewind. Go back. Bing. Right here. You guys see solid cylinder rotating about its center? If you just make that flat and maybe turn it vertical, that is a turntable, isn't it? 1/2 mr squared. So let's go forwards again. Forward, ding. So in place of this I for that turntable, if I know the mass and the radial size, I could do 1/2 mr squared. Okay, this would be a cylinder, flat cylinder shape. Okay? Then times alpha. Then alpha is the rate it's speeding up spinning, the radians per second squared. You guys get all that? Okay. Now, as it's speeding up spinning, it's also gaining another property called angular momentum. That's related to that bike wheel. That's related to that spinning coin, gyroscope, a top. Paul Hewitt with his weights doing the ice skaters, right? Is all involved with that capital L. And I just gave you guys notes and quadrants with that L, right? You guys have all that? Right? And look, it's I times omega. You guys that? Omega is how fast is it spinning at that moment. Which looks like it would probably be changing if this thing is speeding up spinning, wouldn't it? Right. And that's going to lead to, well, let's look at this paragraphs. I know I skipped over a couple slides, so I'll go back to this, right? So can I say I was applying a constant torque to that turntable, and I could do that by a constant force in the string at a constant radial distance, right? And that's what this graph is. Look, torque versus time. You guys see how it's a constant torque, right? Now, you guys know from this class that different properties of a graph could represent different physical variables. It turns out that the area under that curve, the accumulated area under the curve, represents accumulated angular momentum. That's what the delta L is, a change in angular momentum. You see that? Right? So, what if you had the exact same story, but from the point of view of angular momentum? And that's the graph on the right. What's angular momentum doing as a function of time? Say it starts from rest, it's that origin point, right? Well, angular momentum would be increasing at a constant rate. Kind of like the graph on the left, torque versus time, that rectangle is getting wider. The graph on the right, angular momentum is increasing more. Right? And it turns out, and you can see, you can check this with the units also. Right? The area under the curve versus the slope of the graph on the right side. The units match up. So the rate change of angular momentum actually represents torque. Okay. Now, I'm really emphasizing this slide, especially for my AP students, because I'm making a video today for all my classes. And AP, I know when I do AP review, this slide comes up so many times and this is going to show up on their AP exam. Okay, so they have to know the relationship between these two. Okay. So do you guys see a constant torque on the left side? Do you guys see a constant slope of L versus T on the right side? Because they're the same thing. Right? Constant slope of this graph, constant coordinate of this graph. It's the same thing. Right? All right, guys ready for an extension question? Here's a tricky question. What if, here, go back a few. Go back to this, pull a string of the turntable. What if I pull a string harder, 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 harder? So I'm actually increasing the torque as I'm pulling. Okay, you guys get that? I'm pulling harder and harder, so I'm increasing the torque. So if I go back to here, wouldn't torque versus time, maybe it could look like this. What if it's a diagonal line? So it's increasing at a constant rate. You guys see that? Okay. If I had that, you guys ready for a tricky question? So you can get this. What would the graph on the right side look like? And it would no longer be diagonal. It'd be a what shape? Parabola. Oh, you guys got it. Yeah, parabola. Yeah, get that? So if the graph on the left side was a diagonal looking shape, the graph on the right side would be a parabola. Actually, AP has asked that before. Okay. Let's see the ones I skipped over. Go back a little bit. Hey, look, it's the ice skater question. You guys watch figure skaters? They go into slow rotation, they pull their hands in, they speed up spinning, they pull their hands out, slow down. And Paul Hewitt just did the same thing. Stay on the turntable. Okay. So the principle here is that angular momentum is conserved. This angular momentum, that's I times omega. So rotational inertia times angular velocity. That's conserved. So sum of angular momentum before equals sum of angular momentum after. Okay? So before and after moving your hands around. So the picture on the left looks like a large rotational inertia because you've got your mass all distributed out. So maybe you're spinning, but not very fast. That's a small omega. Pull your hands in, you just shrunk down your rotational inertia. Okay? And then force to compensate is that your angular velocity is going to go up. Okay? You guys, does it take some work? Suppose you're spinning. You're on skates and you're spinning. Does it take some work to pull your hands in? Yeah, that takes some effort. Is that energy coming out of your muscles? Yeah, that's where it comes from. So you could also run an energy analysis on this. And guys, where do you think there would be more energy? In the picture on the left or the picture on the right? Picture on the right, because again, it comes out of the skater's muscles. Is where it comes from. It takes some effort to pull your hands in. Right, little thought there. We're not going to quite get to that today, though. Okay, guys, good? Good. Okay. And okay, here's the other one I skipped over. So check this out. Spinning a basketball. You spin a basketball. I've asked this as a midterm question in the past too. Okay. So how fast is the basketball going to spin? Because you give it a knock, it's going to spin like how fast? Right. So here's how you solve that. So torque times time results in angular momentum. Hey, this is the notes I just gave you a few minutes ago. You split the page into quadrants, talking about angular impulse. So that's the starting point for this. Right. And torque, well, what is that? Well, that's this R crossed with this F. Maybe a friction force you apply at the edge, bam, you knock it. Okay, so that subs in for that torque. Right. Angular momentum, well, that could be I times omega. Right, that starts from rest. It would just be I omega. Right. Okay. What next? Well, what is this I right here? Hey, I know where to find that I. Right, I'm going to go back. You guys ready to go back? Bing! Right here. Here's for a spherical shell, which is basically a basketball, right? It's at 2/3 mr squared, right? Let's go forward. Bing! Right here. So in place of this I for basketball, it's 2/3 mr squared, right? And I'm emphasizing 2/3 only applies to this basketball, so I made it orange. Guys, that if this, guys, what if it was a solid foam ball? That would no longer be 2/3, maybe like 2/5 or something different. It would be a different number. Okay, so the 2/3 is only for the basketball. Okay. Anyway, you can solve for omega, which is how fast is it rotating in radians per second. So you do a little algebra shuffle, and here's the end result. And I think it makes sense if you look at it. Okay. So, hey, if you apply more force, does that make it spin faster? Yeah, 3 times the force is 3 times the spin rate, right? In radians per second. What if you apply that force for more time interval, right? Maybe if you knock it 3 times instead of like you knock it once, bam. What if you knock it 3 times? Bam, bam, bam. So like 3 times the amount of time. Right? That'll make it spin faster. Okay. Guys, what if the basketball is more massive somehow? Like use a thicker material or it's more massive. Would that make it spin not as fast? Because it would have more inertia. It's harder to get it to spin up to speed. That's why M is in the denominator. Makes sense. Okay. Now this R is a little tricky because the R there's a competing effect. In terms of torque, more radius gives more torque or allows for more torque. But in terms of inertia, mr squared, more radius is more inertia, so that might make it spin not as fast. And since it's squared on the on the inertia bit, that actually counts more. So the aggregate effect is that the larger radial size ends up making it be able to not spin as fast. Okay, it's a little deeper thing. Okay, guys, that. Yeah, one of the things I want you guys to get out of this class is, can you see the relationships there? Like big picture, forest for the trees, read the music of these equations. Why do it make sense? Again, if you swapped out the basketball for a solid foam ball, I bet that 3 and the 2 would maybe be like a 5 and a 2 or something. Yeah. Yeah. All right, here we go. Okay, a couple more slides here. So this one I have to make a slide because, especially for my AP students, AP asks this almost every year. They always have, okay, you got one stationary disk is lowered onto a rotating disk. What happens? Right? I mean, this question always comes up on the AP exam. So it goes like this. The principle is conservation of angular momentum. So I got a stationary disk. I'm going to lower it down onto the already rotating green disk. Now this one I made it I and 2I. Maybe the green one's twice as thick or something. Right? Right. And the principle is that the two disk system angular momentum is conserved. You guys see that red line never changes? It's constant all the way across. Before and after they stick together. It's always the same. Right? Now, the gold disk was starting out stationary, hence not rotating at all. So it starts out 0 angular momentum. And after 60-degree disk, it's going to get rotating, so now it has some angular momentum. Right? Where to get it from? Well, it sort of stole it from the green disk. So the green disk is going to also slow down. Now there's more mass stuck to it. Okay. And that it looks like this. Do you guys see that every single time location on this graph, the gold line and the green line add up to that constant red line? Is that right? So again, if you were in AP, that would be a question you'd get on the AP exam because they always ask it, right? Right. And last one today. Hey, here's another one that AP likes to ask every year. So AP students, I really emphasize this too, is what if you have a blob of clay and you throw it at the swivel rod? Do you see that X right there, that little pivot point? This rod can swivel around, right? So the blob of clay sticks and the whole thing starts rotating. You say, how fast does it rotate? Let's say, well, if there's a collision, that sounds like something to do with momentum, but it's rotation, maybe that's angular. So is that angular momentum? And it is, but what is the angular momentum of a point mass? How does that make any sense? And this is what it is. So angular momentum for a point mass is very simply just regular momentum mv cross multiplied by radial distance from this pivot point. So r cross mv. And if it hits at a 90-degree angle, which AP always asks, like I've never seen AP ask it at any other angle, then you get 100% of the cross product. So you just very simply do r and v or mvr. That's it, right? Then what? And so how fast does it rotate? Well, that angular momentum then would be I times omega. So you could solve for omega post collision. Okay? But what is that I? Now here's the last little trick. Is this I? See, if the clay stuck to the rod, then it's the clay rod system that's rotating. So you have to do the combined I for both of those. Yeah. So this I rotational inertia would be both the rod itself plus the clay that's stuck to it. Okay. So it'd be a combined I. Okay. And then you could do variations on this. So what if you had a bouncy ball that Lavoie bounced off it or something like that? Okay. You guys see it? All right. So again, that's especially this slide here and this slide here. Actually, some of these slides I'm more heavily emphasizing for my AP students. Okay. And then this concept we're going to save for a different day. All right. So I got one more activity for you guys today, and I'm going to introduce this with Paul Hewitt. We're going to find the center of mass. Here we go.
Hi, gang. Center of gravity time. Turns out everything has a center of gravity. Us, you, me, book, this object, center of gravity of the book, right in the center. Easy to find. How about the center of gravity, something like this? Well, we can find it by hanging by a string. It's somewhere below the string. Hang it like this, somewhere there, huh? Hang it over here, somewhere here. So guess what that point is there, gang? Begin with CG. That's right, center of gravity. We can find that like, see, all three, boom, center of gravity. An object like this, more interesting. Hang it like this. Hang it like this. See that? It's right in here, gang. The center of gravity is not where the object has any mass at all, which is nice. Take an object like this. Where's the center of gravity of that?
Yeah. You guys think center of gravity, center of mass would be like just above this little 2-centimeter wide foot, like probably somewhere right where I'm tracing the mouse cursor? Yeah, because it has to be over the base of support, right? There you go. Right? Now he's saying center of gravity, I'll say center of mass. They're almost the same thing. The difference is if you have a 100-story skyscraper, do you think the gravity field at the top floor is a tiny, tiny, tiny bit weaker than at the bottom floor? Yeah, so the center of gravity might be a tiny, tiny, tiny bit below the center of mass, but otherwise for this class, they're basically the same thing. So here we go. Right. Guys, write on a quarter page. You guys got a quarter page on your desk. Write your name and write center mass lab and put here. You're going to solve 3 of these. Actually, I'll solve one of them with you guys. I'm solving number 9. There are foam boards scattered around the class. This one's foam board number 9. Now, all of these have multiple choice options. One of these dots is the center of mass. I'll show you guys 3 different ways to find it. One way is here, you got the binder clip and the string. You could hang the string. If I was hanging this vertical, it would always hang through the center of mass. If you're not sure if it hangs through 2 points, all you have to do is flip the binder clip anywhere else around the perimeter, and this string will always vertically naturally hang through the center of mass. Right? And if you're not sure again, you can just flip, you can put it anywhere around the perimeter. It always hangs through the center. Right? A second way you can find center mass is turn this upside down. Where does it balance on your finger? Okay, so just scoot this around until it balances. Come on. Probably right there. Bam. It's right on point D. See right point D? Right. So number 9 is D. Number 9 is D because it's number 9. Right. And a third way is what if I take this and I spin it through the air? I check this across the room. It goes into a parabola shape. Look, guess which point it's spinning around? The center of mass. Yeah, which is also point D. Right. So guys, rest of the class, find 2 other foam boards, put numbers, so it's like, I don't know, number 1 and number 3, whatever, 2 other numbers. Find what is the center of mass, turn this quarter page into the gray tray, and I will give you guys lab credit for that. And that is a wrap on today.